No, that's fine. Okay, hello everyone, and welcome to this week's colloquium. And thank you for showing up on this evening. So today we are pleased to have Dr. Yusuke Tampo. He's a new postdoc at SAAO, and he will talk about optical outflow signature in outbursting dwarf novae. Thank you.
Okay, Nargas, thank you very much for introduction. And as the introduce, I am a new postdoc here. SAO class actually also will be uploaded into USIC as well. And just last month, and it's been like about 3-4 weeks in here. And today, as my title says, I'm gonna talk about optical outflow studies in the outbursting dwarf nova system. So before going to the science, here's my just a brief introduction. So I got my bachelor, master, doctor in Japan, and especially bachelor in Tohoku University with Masaomi Tanaka. And at that time, I did more about the extragalactic transient. But after I moved to Kyoto for my master and doctor, I have been working on the cataclysmic variables for about 5 years with Daisaku Nogami and Taichi Kato. And during my PhD, I did some things like presented here. One is about outburst physics in dwarf novae, which I present in a last bank meeting on Tuesday or something. And today I will more focus on about disk length in high-state cataclysmic variables using optical spectrum plus some numerical simulation collaborating with people in the UK, particularly Christian Kniege in the University of Southampton. And as I said, I will be mainly in the SAO building, but I will also be visiting UCT sometime. So please say hello to me if you want me. And also my official supervisor will be David and Pauline here. And besides work, I have been, some like hobbies and other stuff. So just also let me know if you find any similarity with me. Okay, so let me move on to science theme. So as my title says, my main target is cataclysmic variables, which is basically accreting white dwarf systems. And especially in CVs, I will today more or less focus on so-called high-state CVs, which is like SCDs explained by a so-called standard alpha disk model with an accretion rate of 10 to minus 8 10 to minus 8 solar mass per year or something. And in most cases, these high-state CVs are non-magnetic CV system, which means that white dwarf's magnetic magnetosphere is very small and the accretion disk down into the white dwarf surface. And this high-state CVs are generally divided into two classes. One is dwarf novae and the outburst, and the other is novae stars. And the bottom present the typical right curve of them in optical. Left is for dwarf novae, and right one is for the novae stars. And today I'm gonna more or less focus on dwarf novae stars. And this system shows this kind of amplitude, short duration, and outbursts, but their time scales and magnitude scales have a large variety between many subtypes in dwarf novae. And compared to that, novae stars is more or less boring stars because they do not have any outbursting stuff or any big variations. But in terms of like absolute magnitude, accretion disk physics, these two type of stars share lots of similarities in dwarf novae in outburst and novae stars. And the accretion disk in this system are thought to be very identical to each other. And as my title says, today I will focus on the outflows in these systems. And as in many other accreting systems, the outflow in the CVs is also divided into two major class, namely disk winds and jets. And actually the existence of disk winds has been studied almost like 50 years or something from the IUE spectrum. And this is the one example of UV spectrum of them in C415 1550 line. And as you can see here, this system high-state CB show this kind of P-signal profile, which is the very strong evidence that something is going out from the system. And nowadays, this is interpreted as the disk winds coming from the accretion disk, not rather than the white dwarf wind, which is more or less the spherical winds. And the other one, the jets, the existence of jet in the cataclysmic variable is still not very well established, I believe. And here is the right bottom is the optical and radial optical in red points and radial in the blue points. And as you can see here, during the beginning of the outburst, this SS signal showed some sort of a radial transient radial emission. And people like these authors interpret this as a synchrotron emission from a transient jet. And they claim this is evidence, first evidence of jet detection in the cataclysmic variables or in the high-state CBs, actually. But actually, there are some literature that's saying that the other origin could be possible because this kind of radio emission is also seen in the novae stuff, which is more or less the stable system. So I believe the radio emission from jet is most attractive, but I believe the discussion is still not very settled. And today, as my talk says, I will more or less focus on disk winds in the high-state CBs. So this is a very schematic view how disk winds impact on the UV and optical spectrum in the high-state CBs. So the upper two panel is for the UV wavelengths. The left is the one I showed in the previous slides, beautiful P-signal profile in the UV and also low and mid inclination system. But if we see the same UV spectrum, but for higher inclination system, let's say eclipsing system, these systems do not show P-signal profile, but instead they show this kind of strong single peak emission line. Now this is understood as a difference of the quantum density through the line of sight, because if you see the system in low or mid inclination, you're gonna see through directly the disk winds, and this disk winds create this kind of absorption component in the P-signal profile. But if you see the system with a higher inclination, which is basically edge-on, you do not see lots of quantum density and absorption component does not appear on the spectrum. And this UV view is common for novae stars and also dwarf novae. But the optical feature of disk winds has been only surely detected in the novae stars, not in many cases in dwarf novae. So left bottom is the the optical P-signal profile seen in the novae star visit cam. And the red one is the HL4, and blue one is the helium line, which shows very similar P-signal profile to the UV lines. And this is also same for the eclipsing system. We see this kind of strong emission line and single peak emission line in the optical in some novae stars as well. And this is because the single peak emission, not the double peak emission, and the accretion disk is not the main source for this kind of emission, because if we see the edge-on system, the accretion disk usually tend to create double peak emission line, but this is not the one. So at least some other components should be contributing this emission line, and one of the most promising interpretation that disk winds. So this kind of stuff has been already known for years, and especially for novae stars. And here I want to introduce some questions, key question on disk winds in the high-state CBs. And the first one, and I will more or less, address this question during my talk. And the first one is about the wind driving mechanism. And because these high-step CPs are very bright in the UV lights, like oysters or something like oysters, the most promising mechanism is the line-driven winds. And actually, there is some like modeling of the UV spectrum, and the typical mass loss rate found in this observation is about 1 to 10% of the accretion rate. But if we look into the hydrodynamic simulation, like presented in the right, this kind of simulation results in about the mass loss rate of about less than 0.1% of the accretion rate. So here is a huge gap between the observation and simulation. So I believe this is a largest missing point in the this went in the high-step CVs, and I'm not very addressing this point during my talk. But anyway, I just want to introduce this is there's a huge gap between the observation and simulations. And also, this wind has been studied mainly in the UV, so it's not very well understood how the disk winds impact on the optical spectrum of high-step CVs. And as I introduced, especially for dwarf novae, there is still not very much dedicated studies for dwarf novae system. And actually, there are some literature that reporting that accretion disk emission lines or absorption lines coming from the optically thick accretion disk, and some atmosphere of them can explain the most type of optical spectrum dwarf novae. And the other point is that there's still, as I said, the wind feature is detected in the optical and UV, but I believe there is still no very simultaneous observation, and also there is no dedicated simulation to reproduce both the optical and UV wind features at the same time. And the other points that may be interesting for doing this kind of research is the wind response to accretion rate. So there are some researchers that saying, especially in like hydrodynamic simulations, that mass loss rate should be proportional to the accretion rate. So if we got 10% of the if accretion rate changes maybe 1 order or something, the mass loss rate should be 1 order or something as well. But if we just looking into the novae system, which is very stable, so we cannot do this kind of things without seeing the dwarf novae, which is basically a transient event. And lastly, the CB system, high-step CB system, have a very simple accretion disk in the universe. Like we usually do not think about to like relativistic things or the magnetic activities of the central star. So our understanding in generally accretion physics in this high-step CBs is gonna be applicable for many other type of accreting systems. So it should be worth looking what is a link between just high-step CBs and other accreting system. Yeah. So here is my general interest in general interest in the disk winds. And to answer part of these questions, I have been working on optical spectroscopic observation plus some numerical simulations. And today I will introduce my works, especially focusing on one dwarf nova system named V455 Andromeda. And this is actually an eclipsing system found in 2005 or something. And so here is a quiescence light curve and showing its eclipse. And by analyzing this eclipse, we know that its system has an orbital period about 0.15 days, and it has a high inclination, like typical 75 degree or something. And white dwarf mass is about 0.8. And also mass ratio, it's the secondary mass over the white dwarf mass is about 0.1. So basically, its secondary star is something like very evolved, almost brown dwarf donor stars. And one interesting point of this system is that this V45 Andromeda also shows spin period in the quiescence. So it's actually a magnetic system as well, at least in the quiescence. And this system went into outburst in 2007. So here is bottom is right curve during that. And obviously this is like 15 years ago or something, not myself, but my colleagues, my supervisors got a very intense spectroscopic follow-up observations like the arrows showing here. So these arrows are showing the spectroscopic observation epochs using some spectra from SAAO in the Hawaii and also many other observatories in Japan, including some amateur astronomers. And it's also resolution ranges from about 1,000 to higher resolution about 40,000 or something westward, and also we took some time resolved data set. And today, I will just introduce two spectra taken during the outburst. One is very around the outburst maximum, and the other is just middle of the outburst decline. And you can just see my paper for the all discussions, but in this talk, I will more or less focus on these two epoch spectrum. So here is how the spectrum at the outburst maximum looks like. So left bottom panel shows the flux calibrated optical spectrum from, and you see many Balmer lines and also very strong helium-2 lines actually here and here as well. And also its continuum is generally blue, which is coming from the accretion disk. Yeah. And right panel, the black line shows the line profile of helium-2 and HR4, and they typically show some sort of, yeah, typically shows a very strong and single peak emission line. And the upper one is so-called Doppler map. I didn't explain this very much for today because I didn't have many time. But
Mine isn't a good word. She attracts.
Okay, so this Doppler map what says is that this single peak emission does not change its radial velocity. It's the rest wavelength is always on the its central wavelength is always staying the almost rest wavelength, so there is no radial velocities by the motion of the binary stars. So yeah, one interesting thing for this system is that by using the Gaia distance and also inclination plus the standard disk model, which would be explainable for the optical continuum, the estimated accretion rate is about 10 to minus 7 solar mass per year or something, which is about factor of 10 higher than the typical value found in the high-state CV. So this is actually a very bright system in terms of the absolute magnitude and also in terms of the accretion rate. And as I said, we see this kind of very strong and narrow and also eclipse emission lines in the Balmer and He II lines. And this yellow line, yellow dashed line shows some sort of very easy simulation how the spectrum would looks like if this emission line is coming from some sort of atmosphere of the accretion disk. So it's basically rotating with the accretion disk rotational velocity. And if you look into these right panels, it is clear that accretion disk itself cannot produce this kind of very narrow emission line. So we believe this is a very fast dwarf sample that accretion disk winds strongly impacting the optical spectrum. Yep. And to test this interpretation, as I said, I did some collaboration with people in the University of Southampton, especially Christian Koenig, to check if this interpretation is correct or not. So we utilized the radiative transfer and ionization simulation called Python, which is a very confusing name. And we set up a sort of kinematic wind model, which is basically set up some sort of structure in the disk winds rather than importing something from the hydrodynamic simulation, something like that. So there are some sort of parameters describing about kinematics and also structure of the disk winds. And this is how the disk winds simulation looks like. And the important parameters for doing this simulation is the first one is the disk winds, which determines the contribution of the disk to the how the system is generally. And also the wind mass loss rate determines what fraction of the mass is going out as an outflow from the accretion. And this kind of kinematic wind model assumes some sort of wind velocity distribution along this, like this blue arrow. So how the wind is going to be accelerated through the streamline. So there are some parameters saying that, and I'm not going to go details, but anyway, this acceleration law determines the velocity of each cells through the this kind of streamline, and it determines the density of the cell, and it eventually determines how the wind component contribute to the line flux in the output spectrum. And also we used so-called a micro clumping technique to do a clumpy structure in the disk winds. And here volume filling factor is a parameter for this kind of stuff. So if this value is lower than 1, we assume some sort of clumpy winds in the simulation. And in this talk, I will present 2 calculations, namely model A and model 2. And model A is the very classical model of the winds, which is designated to explain the UV spectrum, UVP signal profile in a high-scale CV. So this is very standard, at least very explainable for the UV features in the high-scale CVs. And model 2 is the new model we newly investigated to explain the spectrum I showed before. And the parameters of these 2 models is shown in the bottom table. So model A has an accretion rate of 10 to minus 8 solar mass per year, which is basically a very basic value as a high-scale CV. And mass loss rate is 10% of that. And the parameter related to acceleration is something like this, and alpha and RB, and it do not consider any clumping in the wind. And compared to this, our model 2 assumes a very high accretion rate as implied from the optical continuum. So it's 10 times higher than the model A. And we also assume the mass loss rate of 1 to 10 minus 8 solar mass per year, which is also factor of 10 higher than the model A. But the ratio between the mass loss rate to accretion rate is basically same 10%. And we kept the same acceleration related values, and we also considered a low filling factor of about 0.1, something like that. So this winds can be said as a very highly mass loading winds that has a mass loss rate of 10 to minus 8 solar mass per year, and also characterized by the clumpy winds feature. So here is a result how the simulated spectrum looks like. So it's same. The left panel shows the flux calibrated spectrum, and black is the observation, and white panel is for the H alpha and helium-2 line of the zoom spectrum around this line. And green one shows the spectrum from model A, and this magenta red one shows the model from simulation from the model 2. And as it's clear from this left panel, model A is not explaining any feature of the optical spectrum at all. And compared to this, the updated model 2 spectrum explains something like line flux, line equivalent, whether also optical continuum by within the factor of 1.6 from the observation. So actually, we went out some sort of great researches. We found out this is going to be at least the best simulation results, which is more or less explainable for the observations. But one of the weak point of our model is that although the observation shows single peak emission lines like here, but the output spectrum is more or less flat top the profile. So not explain, it's still not reproducing the single peak profile as observed. And we suspect this is could be more or less due to
Sorry to interrupt, but so your simulation is not just the wind. There's a disk in there as well, right?
Yeah.
So what you're seeing in the simulation results is a disk, and what you're seeing in the observations is not a disk. Or am I mean, I know that's a bit simplistic, right? But that's what's going on here, right?
Okay, so yeah, in the disk model, actually, we think about some sort of temperature of the standard disk model, distribution for the standard disk model, but we consider some sort of stir wind model, stir atmosphere model disk. So it usually produces some sort of absorption lines only. So it does not produce any sort of emission line from the model itself. And yeah, the typical optical continuum is also, so actually this model, this corner model is not something like that. It's assumes some sort of atmosphere on this surface. So it's not very looks like this. I mean, this model does not necessarily looks like this, but in terms of like optical continuum, it should be the same. Yeah, level of the continuum and also gradient that should be the same. Okay, thank you very much. So anyway, so we suspect this difference in the line profile could be due to we believe we can do some updates in the wind acceleration law, and we actually apply some sort of well-established equations that we may need to update this kind of equation, but it's a bit out of focus over research, so we do this kind of stuff. But anyway, we believe that this wind model can generally explain the observed features and much better than the some sort of model with only with the accretion disk. And as I said in the introduction of this object, so this is a dwarf outburst, which is basically a transient event. So we took some spectrum during the outburst, and this panel shows how the spectrum evolved during the outburst. So the top one with straight line is the spectrum actually in the slide before around the outburst maximum, and this dashed line spectrum is what we see more or less 1 week later from the outburst maximum. And if you look into the line profiles, HR4 helium-2 lines turn into double peak profile, and also the line equivalent width also some sort of becomes weaker rather than stronger. But if we carefully check the double peak separation of this double peak emission line, it's still narrower than what we expect from the accretion disk. So as I said, accretion disk would create some sort of 1,000 kilometers or something of the peak separation. But this observation suggests that the accretion disk is still not going to be able to explain these peak separations, but instead, we suspect these winds could be still dominating the emission lines as well as these line profiles. So we have carried out additional simulations trying to model this spectral evolution. And in this simulation, we basically use the same wind model, like in terms of the acceleration, clumping, but we just lower the accretion rate. So the only adjustable parameter was accretion rate, and also we kept saying the accretion rate to mass loss ratio. So it's the same 10%, has the same 10% mass loss rate, and also have every very same wind features. And by adjusting the continuum level, we found that the model was about 5 times 10 to minus 9 square mass per year model is going to be able to explain major observed features in terms of like line flux, of course, line continuum, and also line equivalent width, and more or less the profile. So here is the result of that. Yeah, we adjusted basically the continuum around HR4, and also this more or less explain the optical emission line features, I mean, yeah, flux and equivalent weathers. So all this result suggests that disk winds is the primary component explaining this spectral evolution rather than something changing the accretion disk itself or something. And also disk winds itself is not changing very much, but the primary factor is the accretion rate in the accretion disk. So just this change would be able to, at least in our simulation, is a key factor to explain this observational features. And also we test this wind model for some lower inclinations. Let's say in this case, we present result for the 50-degree, and which is basically a mean inclination cases. And the lower ones show how the spectrum look like if we see this kind of very mass loading wind in a 50-degree inclination 50, and gray shows the case for 75, which is basically model for the V45 Andromeda itself, and red is the one for the 50 inclination 50. So you actually see this sort of absorption line in H beta and also asymmetric line features. And actually this is looks like as the observational ones in some novae stars. So we believe this V45 Andromeda-like winds also could be present in some of these novae stars in the optical wavelengths. And also the left bottom one shows the UV spectrum of C41550 line looks like. And as I said, model A is basically developed to explain the UV. Oh, okay. Yeah, maybe I can just stop here and then, how should I do that? I should just skip it back?
Somebody didn't bear much green.
I think
Unlimited license. Going on.
Yeah.
Okay, I'll just restart the same meeting for the people who are attending online.
Okay, so should I just?
Yeah, let's end it here and.
Mm-hmm. Okay. Yeah, so.
You mean reports?
Yeah, so the Zoom meeting is.
For the people online, as you see, the Zoom is going to